question is really whether people can hear me without it. Can you? No. Well, maybe I'll just start speaking louder. Okay. This strange guy here, Gödel, is really the most fantastic man, really. I think, pretty obviously, certainly the greatest magician of all time. And he was also an interesting man in various ways. Okay, so I don't want to, I will tell a few of the standard stories about him. But really, I want to talk about the mathematics. Or if you like, the logic, whatever you want to call it, which I think is very interesting. And especially, I want to talk about it because lots of people have misimpressions about it sometimes. If you've just sort of half heard of some of these things, you're liable to get a few things wrong. And you know, even quite well-known people sort of get some of these details wrong. So, I'm not really quite sure how to start. Unfortunately, you know, when I gave a version of this lecture at Princeton, I was with all my books, which include, you know, 2 biographies of Gödel, 1 book of reminiscences about him, lots of source books in logic and everything else. And I haven't brought them here, and I must say I didn't sort of do the sensible thing and go to the library and scrutinize these things. So I'm happy to rely largely on my memory. So that means I'll be a little bit vague at some times. But I don't think I'll be vague about what the theorems are such, just sort of when they were proved and so on. And the story really starts just before 1930 with a lecture of Hilbert to the German Mathematical Association, Deutsche Mathematische Vereinigung, where he mentioned 4 sort of fundamental problems in logic that he thought, you know, were very interesting, very difficult, but hoped that some progress would be made about them. And the really rather remarkable thing is that Gödel answered all 4 of these questions. And more remarkably, that some of the answers, probably half of them, were not at all what Hilbert expected. One of them, I think, is perhaps really the most important in a way. And it's not the one that you're probably thinking of, the incompleteness theorem. It's the completeness theorem. So Gödel proved two theorems whose names are the completeness theorem and the incompleteness theorem. It looks as though they contradict each other. But they don't contradict each other at all. And rather funnily, the completeness theorem tends to get missed off a lot of the discussion because the incompleteness theorem is so much more exciting. But in a way, the completeness theorem is, you know, more important and more fundamental. It's also actually rather easy. But they're talking about different things. The completeness theorem is talking about logic. And to be more precise, it's talking about what's usually called first order predicate logic. But don't worry too much about that little technical qualification because it's really talking about logic. The incompleteness theorem is talking about arithmetic. And perhaps I could put in some little sort of qualification there, but really it's not so necessary because any kind of arithmetic that deserves the name of arithmetic is covered by the increment statement. I think it's interesting that, I mean, what it says is that the methods of logic over here are complete, that we actually know all the methods of proof. You know, that a logical statement is true, which actually is slightly better to use the word valid, if and only if it's provable from the standard rules of predicate logic. Over on the other side, arithmetic is incomplete in a very, very strong sense. If you have an arithmetical statement, that's a statement about ordinary sort of positive integers or something, you know, with usual operations of addition and multiplication and logical symbols mixed in, then not only do the sort of standard rules of arithmetic not entail everything that's true, but there's no way of codifying arithmetic, you know, no system of rules whatsoever that will guarantee to prove all arithmetical statements. Now, I think one sort of reason why it's interesting to observe, you know, that the same man proved both theorems, and that both theorems are true and that they're sort of opposed to each other in a certain sense, is that earlier in this century, there was this great logicist, movement or thesis or principle, whatever you want to say, which is that arithmetic reduces to logic. Or more generally, mathematics reduces to logic. In other words, that if you know all about logic, then you know mathematical statements just sort of follow automatically. Here we're sort of seeing that arithmetic obviously doesn't follow from logic. Well, what's the? I mean, this thesis nonetheless has a certain respectability, you could say. Russell espoused it particularly. But let me point out that something's changed. As a consequence of Gödel's theorems, we now understand the term logic rather differently. It's sensible to redefine logic to be essentially what's written here, which I'll try and explain, precisely because we have the completeness theorem. You see, a logical statement, I mean, a logical proof, whatever we want to say, how can I say? People always used to say that logic was the science of drawing necessary conclusions about subjects which you sort of don't necessarily know about. So you know, we don't inquire whether what do we say? Dolphins are fish or mammals, but we do know that if dolphins are fish, then something else. You know, in other words, we don't inquire about the hypotheses. We just inquire about whether the conclusions follow from the hypothesis, whether we make valid deductions. And what Gödel discovered was that yes, the following rules, and I'll sort of just give a few of them, actually do suffice for making all universally valid logical deductions. So first I'm going to put up hope you can just about read that. It doesn't matter terribly much because I'm not going to refer to it in tremendously great detail. These particular few statements here, perhaps it'll be more legible if I move them down, are just about the logical connectives and or. And for and, I'm going to use this standard ampersand symbol. Or, I'm going to just use the English word or, but one should perhaps use a symbol. And so what we have in the modern notion of a formal system, you have strings of symbols. about whose meanings you don't inquire. And you write down a number of rules to say when one string of symbols entails another, or to be more precise, when a whole collection of strings of symbols entails another collection. And here are a few of the rules for what's called the propositional calculus. So in the propositional calculus, these letters like P, Q, and R stand for propositions that we might not sort of bother to analyze their meaning of in detail. Whatever they are, we don't terribly worry. P might be that a dolphin is a mammal rather than a fish. But look, if you can deduce R from P, then suddenly, if you understand the meaning of the word "and," you should be able to deduce R from P and Q. Because P and Q should mean just that P is true and Q is true. And similarly, if you deduce R from Q, then you should be able to deduce R from P and Q. Well, I've given sort of verbal arguments that sound like a proof of those things. But really they're definitions. And what we do is we enshrine those two principles that I've written up in black at the top there. And what they help to do is make sure that this little ampersand symbol, "and," really does mean "and." Okay? Because, it's probably easier to see that from the red statement below. If R entails P and that's the English word "and," R entails Q, then we're entitled to say that R entails P and Q. Well, what actually happens is, for each logical connective, there are really two statements, one red and one black, except that sometimes, I split things into two parts. So, here the black statement is that if either P entails R or Q entails R, then P and Q entails R. And the red statement is if R entails P and R entails Q, then R entails P and Q. Those together suffice to make sure that the logical symbol "and" has the same effect as the real English conjunctive "and." You can deduce P and Q if and only if you can deduce P and you can deduce Q. And then similarly, we have at the bottom the two statements that make the logical symbol "or" have the same meaning as the English word "or." And you'll recognize these as principles that you actually use in mathematical arguments. Okay? And so you'll sort of search about them. What you don't recognize, perhaps, is that these, and a few others like them, which can be explicitly written down to cope with the other conjunctives, comprise all logically valid methods of argument. Okay? That's Gödel's completeness theorem. I have missed off the ones for the negation of a proposition, or the denial, perhaps is a better word, of a proposition, and the ones for implication. But they're rather similar. In each case, you have two basic statements. One, the one I've written in black, is usually called. This one here is "and out." And this one is "and in." Well, it's rather easy to explain. These are names for these two statements. It's rather easier to explain the bottom one. It tells us how to get "and" into the conclusion. Well, getting something out of the conclusion is the same as getting into the hypothesis, and that's why the other one is called out. So what happens is, for each logical connective, there's an "in" statement and an "out" statement, or should we say an "in" rule and an "out" rule, that enable you to take that connective from the hypotheses and put it into the conclusion, or vice versa. And, okay, well, I've only talked about the propositional calculus so far, but it's really rather important to talk about the predicate calculus. When you talk about the predicate calculus, you will have things called predicates, and a predicate is written in P of X, and it's a proposition. I mean, its sort of intended meaning is that P of X is some kind of proposition about a variable X. So you have two kinds of symbols now. Letters like X and T and so on that correspond for objects, and things like P of X or P of T, which corresponds to a statement involving the object X or T. And here are the fundamental rules for the in and out rule, which is called the universal quantifier, which means for all T something happens, and the existential quantifier. And if you look at them, they're very similar to the, I just thought of a way of explaining a bit of illustrating the two right here. I'm going to cut this thing into two here. I'm going to cut the original one into two as well. And then you'll see that the universal quantifier is very like and the existential quantifier is very like or. So here at the top I have the rules for and at the bottom I have the rules for all. So you see, think of P and Q as just two cases of a tremendously general proposition, with general cases P of T. And then what you want is that if P of X entails R, for any one of all possible X's, then the statement for all T. Now, if any particular P of X entails R, then certainly if P is true for all T, then that entails R. And that's exactly like, say, if P entails R and Q entails R, or Q entails R, or any other case entails R, then P and Q entails R. And look at the bottom one. At the top it says that if R entails P and R entails Q, that is to say R entails all the cases, then it entails it. So here we have to sort of make little assertions about exactly what the symbols mean here. So look here, these little things I put in green. If there's any X at all, it might be 17. It might be Charles. Any object at all for which P of X entails R, then if P is true for all X, that entails R. Because, that helps to make sure that this symbol over here does include P of X for every particular X. And then at the bottom here, if R, which doesn't mention T, entails P of T, then it will entail P of anything. If it entails P of just a dummy variable T, then you can go through the argument by which it entails up T and substitute any other symbol for T, and so it should entail for all P of T. Once again, I've given sort of English arguments to suggest that these things are true. But the real thing is they're definitions. And a very similar thing happens up here. Let's just put it on. Here's the here's the or and the existential quantifier. So here, if any one of the two cases P and Q entails R, then the disjunction P or Q entails R. And look at that at the bottom. If P of T, I think I've got that around. Oh yes, now if every one of P and Q entails R. Sorry, I said it the wrong way. And now here is if P of T, without even being told what T is, entails R. That's to say every P of T entails R. Then the existential. And when you actually look at the qualifications, there's a beautiful duality which is part of De Morgan's laws, properly understood. Look, the red thing for all is the dual of the black thing for and similarly, vice versa, the black thing for all is the dual of the red thing for and. And when we look at the universal and existential quantifiers, you find the same stuff. The black rule for the universal quantifier has the same little green annotation as the red rule for the existential one. Anyway, never mind. I spent much too long talking about this. Well, okay, imagine those rules written down, and you'll find them written down in any number of pieces of logic books, for instance, King's Introduction to Mathematics. They take a page. And it's a really wonderful fact that that page encompasses all logically valid arguments. All arguments that are valid, no matter what the predicate symbols actually mean that we're talking about. And that's Gödel's completeness theorem, which he has two technical ways of stating it. One is semantic. That's to say, it's talking about the meanings. And what he has there is that any any statement that's deducible from the rules is automatically true in all models. What a model means for a collection of statements is that you assign particular objects to all the things called terms, like x and t in those statements over there, and then you assign relations between those objects to predicates. Okay, and obviously the sort of English arguments I gave to justify those things say that if something's deduced from those rules, it's actually true in all models. And the converse is that if something's not deducible from those rules, it's not true in all models. That's to say there is a model in which it's false. And that's really the completeness theorem. And it can also be stated purely syntactically, which just sort of says, well, never mind, I won't bother to say this. Okay, so that's the completeness theorem. And I think it's an absolutely fantastic theorem. Now let me move to the incompleteness theorem for a moment. So the incompleteness theorem is probably more familiar to you. There what you actually have is arithmetic. You have a language, a formal system for talking about arithmetic, and so some of the constants and terms and so on will be restricted to numbers, and you might have a statement like, for all n and for all m, n equals n implies n plus 1 equals n. That's actually one of those axioms. I'm just writing it down to give an impression of what the typical statement of number theory will look like. It will have a few of these quantifiers in it, some equal signs, a function of arithmetical operations, and some Boolean connectors like implies and so. Okay. And now, the really fundamental difference between logic and arithmetic in this sense is this, that in arithmetic, we think we have in mind a standard model, which is the collection of ordinary integers, whatever they are, in which, addition means addition, and equals means equals, and various other things mean what they usually mean. We think we know this particular one infinite model. Okay. And now, suppose that's true for the moment, what we all tend to believe before we get logically educated anyway. Then, it means something to ask whether a statement is true in this model. I mean, how about this one? For all n greater than equal to 3. No, that's not true, because 2 isn't greater than or equal to 3. So this one is false. This one, however, is true. Now, these concepts, truth is a sort of dirty word in logic. This notion of true refers to the particular model we have in mind. Okay? We sort of test it against the model we have in mind. In logic, we don't have in mind any particular model. This statement is a statement about all models. Okay. And that's a very, very fundamental difference. Okay. But then, if we write down enough axioms, like this one, we would hope to be able to capture all the true statements. Axioms and rules, which would be the rules of logic, for deducing statements from each other. So, we write down some axioms that are true for the ordinary integers, and then we employ the logical rules that are true for all logical systems whatsoever. And we would hope to be able to get a complete system of axioms for arithmetic at the same time. Well, Gödel shows that we can't do that. Let me just recall briefly how he does it. What he does is he starts numbering all the possible sentences you can write here. Except that he actually takes the ones that involve a free variable. So let's just have, x greater than or equal to 2. This involves a dummy variable x. It hasn't been, a free variable x. It hasn't been quantified out as this might be statement number 17 about x. Hope you understand what I mean by that. And we enumerate all the statements. I'll start with S1. I usually prefer to start with S0. So I'll start with S0 x, S1 x, S4 x. He sets up a mechanical system such as you might use in a computer that enumerates these statements. And then he asks the statement, then perhaps I should say, he also sets up a list of proofs, P0, P1, P2. So these are proofs. And these are statements, but they're really statements about x. They've got one particular free variable. These are all statements about x, and these are all proofs. Now, what's a proof? Well, a proof is just a sequence of strings of symbols, such that each string of symbols is deduced from previous ones by these logic rules, or it's an axiom. So, a formal proof is quite a precise concept, just a string of strings of symbols, and therefore you can sort of enumerate them. And Gödel writes down explicit enumerations of them. And then you consider the following thing. The P proof is a proof of the S statement about the nth number. So what does this mean? S of 3 means what you get from S of x by putting 3 of x. So when you look at this, at the moment I'm just thinking of this as an English sort of statement here, that the piece one of these proofs is actually a proof of the nth statement at the nth number. This is how can I say it? This is an assertion about 3 numbers, namely P, S, and N. Okay? Now, the interesting thing is that this is not just any old kind of assertion about those scheme numbers. It's one that's sort of very precisely checkable. You see, if you know exactly what the enumeration of proofs and the enumeration of statements is here, you can set your computer to ask whether the piece of proof is a proof, you know, of the nth statement as n. So this is an arithmetical assertion. Well, arithmetical means roughly programmable by a computer. Now it is a fact that if the usual formal systems for arithmetic have the property that anything that is programmable by a computer can be written in the system. So is equivalent to some statement, I don't know, what shall we call it? Well, Gödel calls it a device, BEW, here. But I suppose I would call it Kura, is the corresponding thing. Writable in the system. In fact, to write it in the system we're talking about boils down really to writing a computer program to do it, and then, you know, codifying the computer program in terms of numbers. Okay, but now I want to consider this one. So it is not, there does not, let me write that, there does not exist a P such that proves P X. And that's supposed to be the arithmetical way of writing down this statement, and now I've put a quantifier in here. That's a not sign. What this means is, i.e., meaning there isn't a proof of the F statement about X. And therefore, so is there does not exist a P such that the P proof proves the F statement about X, i.e., there isn't a proof of SX of X. And now, this is the wonderful statement that some of us call Gödel. Let's have a look at it. This is a statement that just has one free variable in it, X. This variable here is a dummy variable, it's been quantified out. So this is one of our list, and by the list I mean that list. Say S73 of X. Whatever this statement is, it's a statement that just has one free variable in it, and that's the variable X. So I'm entitled to call it S73 of X. And now you look at S73 of 73. I mean, the game is, you know, you look at this statement and you find it somewhere in this enumeration. And I'm just going to suppose it's the third one. And now look at S73 of 73. It means, well, I'm going to talk about this question of meaning in a moment. So what does meaning mean? It means S73 of 73 isn't proven. Or in other words, i.e., I am not proven. Where it's not me that's talking, it's S73. Okay. Well, now, what on earth do we mean by me? Well, this is quite a big deal. This statement doesn't mean anything of the kind. It's some horrible statement. It sort of starts off by saying, for all it says there does not exist a P. But then it carries on, for all the existences of all the, etc. And then there's all sorts of stuff. So this is what S73 of 73 looks like. I don't want you to get a wrong impression about this S73 of S73. It doesn't say I'm not provable. No, it says that does not exist a number P such as all numbers A, all numbers B, that exists a number C, such that all this arithmetical jazz holds. It's a purely arithmetical statement about integers. So what did I say then? I said it means S73 of 73 is provable. Well, it doesn't. It just means that there are or are not integers like this. And however, we can recognize that it's true as a matter of fact, if and only if S73 of 73 has no provable system. Because all this stuff in here is an arithmetical coding of the existence of the proof, or the non-existence. So we recognize from the outside, having done things, that this statement is actually true of the integers, if and only if S73 of 73 is not provable. But this statement is S73 of 73. So this statement is true about the integers, if and only if it's not provable. Okay. So what do we deduce from it? It's true. Let's call it G. G is true if and only if G is not. And what does not provable mean? It doesn't mean it doesn't have any proof at all. In fact, we just seem to prove it. That's a little worrying. It means not provable in the system of axioms and rules. You suppose we have some axioms and some rules and so on. So let's just call that the formal system S. G is true as a matter of fact about the integers, if and only if it's not provable in the formal system S. So what can we deduce from this? Well, we can deduce that if the axioms and rules of S are actually true about the integers, then this damn thing must actually be true. And let's explain why that's the case. You see, we ask whether it's provable. I don't know. But if it is provable, then it should be true. If we're supposing that the axioms and rules are okay. If it's provable, it should be true. But if it's true, then since what it says is it's not provable, it's not provable. So if it's provable, it's not provable. And that's a contradiction. So it can't be provable. But that's just what it says, so it should be true. So, if S is okay, then G is true, as a matter of fact, but not provable. Okay. Now what do I mean by okay? Well, when Gödel first proved this theorem, it meant a rather technical, messy thing called omega consistency. And a little bit later, Rosser found a trick which produced that straight consistency. So I'm going to strike off this and not add any more argument and say if S is consistent. And that means if you can't deduce 0 equals 1 in S, or equivalent, if you can't deduce a statement and its negation in S, then it's true. Okay. So some people, Roger Penrose for instance, think that this counts as a proof of the truth of the statement G. Well, it doesn't. It really very definitely doesn't. What it says is it's a deduction of the truth of G from the consistency of S. Okay? And indeed, that's Gödel's second theorem. You see, if S is consistent, G is true, well, you know, we don't bother to say is true. When we say G, we mean G is true. If S is consistent, then G holds. And if S is not consistent, G is false. Let me leave the is true and is false. We do have a bit. If S is not consistent, then what actually happens? Well, if S is not consistent, everything is provable. If you're given a statement and it's negative, you can deduce everything. There's a famous story about Russell, who was talking at a high table in Trinity College, Cambridge, about this principle, given something that's wrong, the whole statement, you deduce everything from it. And somebody said, okay, I give you that 4 equals 5, you prove that McTaggart here is the Pope. And Russell, quick as a flash, said, okay, 4 equals 5, subtract 3, you get 1 equals 2. McTaggart and the Pope are 2, therefore McTaggart and the Pope are 1. You don't have to have that particular argument. It's a well-known principle in mathematics that given the statement and its negation, you can deduce everything. And therefore, if S is inconsistent, every statement is provable. And in particular, G is provable. Okay? And since G says that it's not provable, G is actually false. So, we get this rather wonderful fact that if S is consistent, then G is true, and if S is not consistent, then G is false. In other words, what we've proved is that the consistency of S is actually equivalent to G. Okay? That G is true if and only if S is consistent. Now, what Gödel's second argument does is say that argument we've just given can actually be formalized in the system S. This time you write down a formal statement that says that S is consistent. That says there isn't a proof of naught equals 1. That's one of the things we could easily write down in an arithmetical statement. Then that arithmetical statement is true if and only if this particular statement G is true. And so we get this wonderful theorem that we can actually replace G by the consistency of S, an arithmetical statement. And so we get that Cons of S is true if and only if it's not provable. How can I say? It's provable in S. If and only if it is actually false. This should warn us against the sort of habit of equating provability with truth. Gödel's great theorem says this particular kind of statement has this marvelous property. So it's only provable in the system if it's actually false. That's provided S is consistent. Okay, so that's the incompleteness theorem. No matter what formal system S we started with, there are two statements. If it's consistent at all, there are two statements not provable. Okay? However, we can never exhibit one. Okay, I mean, we can never prove the truth of such a statement. That's where people go wrong. You can guess that your system is consistent, and then if you guess your system is consistent, then that's just the same as guessing that G is true. Okay? We don't prove that G is true. We prove that G is true only if the system is consistent. If you guess the system is consistent, you're guessing this statement is true. Well, let me pass on rather quickly to a few other things that one that immediately follows from this is the predicate logic, which he just proved was correct, so to speak, was complete, is not decidable. Now, this is an absolutely amazing thing. It shows that there is no guaranteed method for proving statements, even when they're not provable. Because every true statement in predicate logic is provable. That's a complete statement. And here's the way that Gödel does that. What you do is you take one of these Gödel statements in arithmetic, and what am I trying to say? You see, a proof in arithmetic, yes, I'll only describe it very briefly. A proof in arithmetic only mentions finitely many cases of Peano's last axiom. Peano's last axiom is really an axiom scheme. It says, for every property of integers that's true of 0, and has the property that if it's true of n, it's true of n plus 1, then all such things are true of all integers. And it's an axiom scheme because it's one axiom for each choice of the predicate we're talking about. You can't express the thing, the fact that it's true for all predicates in this predicate logic. You just say for each predicate, but any particular proof in arithmetic will only use finitely many cases of that. And so that proof can be written in predicate logic. What you do is you write down the conjunction of all the cases you've used, which are only finitely many, as a hypothesis in logic, not in arithmetic. It sort of says, if you've got a system that satisfies this number of particular cases of the induction axiom, then that's the dot. Oops. Did I touch that? So any proof in arithmetic only actually, it can be written as a proof in logic, basically. And the fact that we can't get, the fact that arithmetic is undecidable, which is one of the consequences, which is rather more easy of his incompleteness theorem, now entails that logic is undecidable. There's no guaranteed method of doing it. That's really we've spoken about before. So we get the wonderful conclusion that logic is complete but undecidable, arithmetic is incomplete and undecidable, and everything else. As I was saying, that's a really good reason for restricting the word logic to refer only to this kind of logic, rather than let it include set theory, as mathematicians earlier this century did. Because set theory includes, in particular, arithmetic, and is therefore undecidable. We've got logic straight. It's an absolutely wonderful feeling to those who sort of get jaded by these theorems. I mean, the incompleteness theorem says we'll never get arithmetic straight. We'll never know. Set theory, there are all these paradoxes and everything. We don't know that the axioms are right. You know, we don't know that they're consistent because originally they weren't, and we don't know whether they suffice to express everything that's true of sets, whatever sets means. We have no clue about set theory. Okay? We don't have much clue about arithmetic, although we're a bit brighter about it than we are about set theory. But now, that's the sort of way that a lot of things have gone this century. It's been very depressing. So here is one theorem that says we got something dead right. Logic. We actually know what it means to say that one statement follows inevitably from a number of others. We've got logic right. And so that means that, you know, this particular subject deserves a name, and the name is logic. In other words, what I'm trying to say is we should not use logic to include set theory. We don't understand set theory. Okay. Let's talk about Gödel's contributions to set theory. So mentioned last time, or probably is the time before really, Cantor's wonderful ordinal numbers. Now these are all finite and distinct. Well, let's just say what I'm writing down here is the correspondence between ordinal numbers and cardinal numbers. And then, if you remember, a tremendous number of these ordinal numbers, and one's naive thought at first is probably all of the infinite ones have the same cardinal number, as not. They're all what we call Cantor. But Cantor showed that the collection of all of these, which is really the next one, is not Cantor. It's got a new size, which is called Aleph 1, and the first number of size Aleph 1 is called omega 1. And then there are lots more, and I've compressed this enormously, because the present number of things in here is actually 2. And then these cardinals continue onto this blackboard, so you get Aleph omega, and then Aleph omega plus 1, Aleph epsilon, and then Aleph one, so on and so on. This, by the way, is called omega naught to sort of enable it to fit in. I want you to notice something. That omega naught is very much bigger than naught. It's infinite. And that omega 1 is very much bigger than 1 because it's even uncanny. And omega 2 is bigger than 2. But there are some numbers that are actually their own omegas. I'll give you. Omega. So, you know, it's handy to sort of confuse Aleph naught with omega naught and Aleph 1. If I allow myself to confuse the notion of a cardinal number, which some people take to the definition to be the first ordinal of its size, then you could sort of say Aleph equals alpha. These are horrendously large numbers. The big problems are, the question is, one, can every set be counted? I.e., is every, let's say, is the size of every set one of the others? That's called a well-ordered problem, because the sets that can be put in 1-1 correspond to those ones can obviously be well-ordered. And Zermelo proved, but really Cantor knew it. Zermelo was a student, by the way. The axiom of choice implies this well-ordering. The assertion that every possible set can be well-ordered. Not only that, it was proved a bit later by Hartog's, well, once again, Zermelo half knew it, that the well-ordering theorem implies the axiom of choice. And what's the axiom of choice? The axiom of choice says if you've got a whole collection of sets that are non-empty, there's a way of picking one element from each one. Let's suppose that it's joint. So if there exists a set which takes one element from each other. That seems, when you first look at it, obvious. It's obvious. Well, how do you get to this obvious? By appealing to your intuitive notion of what the set is. We all seem to think it's obvious, but it's not deducible from the more obvious axioms that Zemela wrote down. And so, okay, well, he wrote down this one, and no argument was raised about it. People discovered that the axiom of choice had been used quite a few times tacitly by people before Zemela codified it. Zemela did the great service pointing it out as a new principle, unlike the others. And the interesting thing is this: nobody has ever been able to exhibit a well-ordering of the reals. In fact, now it's been proved that you cannot exhibit a well-ordering of the reals. There's no possible definable well-ordering of the reals. And so if you believe there is a well-ordering of the reals, you're believing something pretty shiny. Something you can never sort of actually, believing in the abstract existence of something you can never go by. Or maybe that's what Shakespeare is about, this sort of existential kind of assertion. Sorry, I'm very, I do want to say that. Well, Gödel's next great discovery in 1939, or I think even 1938, was his proof that the axiom of choice could not be disproved with respect to the other axioms. That's to say, if you deduce a contradiction from the other axioms of set theory, then, including the axiom of choice, then you can deduce a contradiction without using the axiom of choice. It doesn't add any extra contradictoriness. It's just as safe to add the axiom of choice as you were before you. And that's really very interesting because the axiom of choice had raised all sorts of questions in people's lives. It really seemed dangerous. And that position changed completely. I think everybody but Gödel would have thought that that was false, before Gödel. The axiom of choice did raise excellent requirements. But then the next statement is the question, well, okay, big boy, when they call you that, actually, it doesn't really deserve the name, because it's quite small, but never mind. Let's say make up address it to Cantor. If you believe that every set can be well ordered, in particular if you believe the reals can be well ordered, what's the size of the reals? Which one of these numbers is it? And that's the continuum hypothesis. Cantor conjectured that it was valid one. In fact, not only did he conjecture it, he said he proved it in the proof of the theory was next, and then he never did. Well, Cantor proved that you cannot disprove the continuum hypothesis either. States right. There's a very great difference here, though. It doesn't seem to be true. It seems as though the real numbers are much bigger than I1. And indeed, when Cohen came along, that was shown to be consistent as well, as opposed to the bigger number. So the continuum hypothesis is rather different from choice, in that the experts tend not to add it to the list of axioms. Okay. I've forgotten to tell all the funny stories about Gödel. Let me say he was a very strange man. He was very friendly with Albert Einstein, and that gives me an opportunity to put, except that I can't find it, a picture of the two of them together up here. Often seen together. There are lots of funny stories to tell about. I met once Elaine Brouwer, the widow of Alfred Brouwer, famous mathematician, and she took me into these gardens, got the name of them, and held me for an afternoon, absolutely entranced, with all sorts of stories about Gödel. She was very close to Gödel. Let me just tell you a few of them that are really quite well known. Gödel, he was very odd. He tended to apply to real life some of the ideas of his mathematics. And when he was going to be naturalized as an American citizen, he went along with Einstein and Morgenstern in the train to Canton, and he was very excited because he said he'd just discovered an inconsistency in the US Constitution. They sort of tried to calm him down and said, well, don't for God's sake mention that. But when he did get there was some discussion about politics. You must remember this was at the time of Hitler and terrible things going on. And the British discussed a little bit of politics with them, and said, you know, that how sad it was that Germany was now a dictatorship and so on. Unfortunately, that couldn't happen here. And Gödel said, oh, on the contrary. And tried to outline his principle whereby perfectly legitimately, at every step in the course of the Constitution, the USA would be changed into a dictatorship. Well, that's one story. He became convinced later in life that people were trying to poison him, and the strange noxious gases were leaking from his refrigerator, and so on. And he eventually died by starving himself. He sort of refused to, after his wife died, he refused to take almost any food because he distrusted it, and so he eventually starved himself to death. A very strange man. I was very fortunate to meet him just once, and it's very nice. He treated me a lot by saying something nice about the square numbers. And what he said was that he had always had the opinion that the true solution to things like the continuum hypothesis would depend on the correct definition of infinitesimal numbers. And he said, well, the surreal numbers seem to be something to do with it, but it doesn't seem. By the way, he expressed this opinion in print. But he said, you know, the surreal numbers do seem to be the correct definition, but they don't seem to imply anything about the continuum hypothesis. So I've got. Let me tell you another story. I lived just behind the Princeton Cemetery for a number of years, and I had seen in one of the biographies of Gödel a picture of his tombstone in the Princeton Cemetery. And this inspired me to go and look for the thing. So I wandered a few times. What I learned principally was how big the Princeton Cemetery is. And then they started locking every door except one particular one. So that meant if I were to look at it on the way home, I had to climb over the fence when I got to the far end where my house was. And one day I was walking in with my mathematical friend Simon Norton, who was visiting me, and I saw that one of the sign gates was actually open because they were doing some work in the cemetery. So I said, come on, Simon, I wanted to find Gödel's gravestone forever. Well, we wandered up and down there for about 40 minutes before I finally found it, and I did. And then we stood and said some super reverential things, which I won't bore you with. And that's that. It's very near to von Neumann's gravestone, which is rather nice. Einstein isn't actually, he's a little bit faint, and I think he's the wrong way out. Yes, he's buried with his wife, Gödel, and who died before him, as I just mentioned. A very interesting fact, since, you know, he sounds like a nerd or a geek or something, is his wife was actually a dancer.